Welcome, chemistry. We are going to finish off our topic on quantitative analysis. Today, we're looking at gas laws. And instead of you guys knowing each of these laws individually, I mainly want you to be able to do the calculations and use the gas law that the ideal gas law we'll look at the end. So firstly, I'm going to go quick through this. We've looked at gases and we've looked at their properties, and now what we're going to do is just see how that plays out in stoichiometry. So there are 4 gas laws here. I didn't put the ideal one down. I should put that down. Ideal gas law. And the ideal gas law is the last one. It combines all of the gas laws into one handy equation. So it's ideal universal gas law. It is PV equals nRT. Okay, so that'll be the last thing we do. We'll get to that. You don't need to memorize it because it's on your data sheet. So firstly, we're looking at the law of combining volumes of gases. And this was developed by Lussac, a French, if I remember correct, a French scientist, and looked at the gases. Now, he did this before Avogadro came in with his ideas of, how many particles are in there. So this is where we're just going to do this pretty simply. Basically, what he said is in a gas relationship, the volume of gases are in equal molar relationships. So the ratio, whole number ratios, at so they follow whole number ratios the ratios of a balanced equation. So the reason why this is important is because this was found out before we knew about, particles and balancing equations. So this came before that, and so now we kind of know basically they follow the ratios of a balanced equation. So for example, if I have, let's make water, H2 plus O2 makes H2O. Okay, that's not balanced. If we balance it, we realize for 2 oxygens here, I need 2 oxygens on our reactant side, product side, and then I need 2 molecules of H2 here. We actually often represent it like this. There's my H2, here's my O2. Oh, everyone loves red. They usually color it red. Let's color it red. There's my O2. And then that will make 2 H2Os. I just stuck them together. Okay, there's my oxygen and my hydrogens. So you'll notice that this, we've learnt it as, it tells you the ratio of the particles. So you can see that. Why is that not coloured in so well? There we go. Okay, anyway, so what he actually observed, Lussac, is that if he, Okay, so that if he had 100 mils of hydrogen gas, it would take half that amount, 50 mils of oxygen gas, and he would make 100 mils of water as a gas. So, and this is all for gases, by the way. Gas, gas, gas. This is what led to Avogadro going with his law about the amount of particles in the same volume. Now, just notice, by the way, set temperature and pressure, because we've already looked at the fact that as we heat gases, they expand. Heat anything and expand. The particles move apart, so the gas volume will expand. And also pressure, you can compress and expand the volume, and so the pressure on the gases is different. So you do need to realize we're keeping the temperature and pressure the same in this case. Okay, so we can still see this as a 2 to 1 to 2 ratio. Okay, if we divide it by 50. Okay, so again, if you were given a question where you were told, if you were told you had 3 litres of hydrogen gas, how much oxygen gas would you need? How much hydrogen gas would you make? And the way you would do this is you would go, okay, well, I know my volume of H2 is 3 litres, and I know that my volume of H2 equals my volume of H2O in this, so that means I have 3 litres of H2O. And for my volume of oxygen, I know it's my volume of hydrogen divided by 2. Okay, and so that will be 3 divided by 2, which is 1.5 litres. Okay, so that's the law of combining volumes, and that just makes it a lot easier. You don't have to convert to moles, because the moles are the same volume of gas. Sorry, that's a little. The same volume of gas at the same temperature will have the same number of particles. Okay, so this then brings into Avogadro's law. Okay, that equal volumes of different gases at the same temperature and pressure have the same amount of have the same amount of particles. Now I just got to go here, just making this as I go along for you. Okay, so what this means is that if I have hydrogen gas, I have 1 litre of hydrogen gas, I have, here we go, draw, erase. Okay, I have hydrogen gas, I have oxygen gas, I have nitrogen gas, I even have carbon dioxide gas. Okay, these are just containers. So these are all 1 litre, let's say. This is just, an example. So our volumes are the same. You have, the same number of particles in the same volume. So oxygen, I'm just drawing 2 in each of these. Now, obviously, if you can remember anything about our Avogadro's, what he found out is you'll know that there's not 2 particles, there's Avogadro's amount, and that's where we're going to get into the law of molar volumes. Will be in a little bit. Let's do this. Black, because that's carbon in there, and rainbow. Oh, nitrogen can be rainbow. No, let's make it a different color. Whoops. I don't know what I just did. Okay. Blue. Blue. Okay, so there's the blue. Nitrogen. Why am I colouring it? Doesn't matter. All right, so we have our different gases. So we have equal volumes. So same volume, same number of particles. Okay, that's Avogadro's law. And we know Avogadro's number is 6.022 times 10 to the minus 3. What I'm going to do is just grab up this. So this is something I copied. This is one of your worksheets. Okay, I'm going to copy it. You saw it before. I'm going to paste it in here. So this leads us to molar volume. And what this is 1 mole of gas at a set, and so at temperature and pressure has the same volume. So 1 mole of any gas. Now, we actually know the volumes, and you're given 2 of them. Again, this stuff is given on your data sheet. So don't go and memorize it. You also have Avogadro's number. Okay, so that means that if I have if I have 1 mole of gas and it is at, so O2, and the temperature is 25 degrees Celsius and the pressure is 100 kilopascals, then the number of particles remember that's the notation for it, capital N, is going to be equal to an Avogadro's number. Okay, and that is 6.022 times 10 to the 23. Okay, so if I have 1 mole of H2 at, and this is called standard laboratory conditions, SLC, at SLC, I will have the number of particles will equal the number, Avogadro's number, and that was 6.022 times 10 to the 23. Okay. Another thing we can know is we know the volume. So the volume of H2, 1 mole at standard laboratory conditions, the volume I have is going to be equal to 24.79. So if I have 0.79 litres here, I have 1 mole of H2. But if I have 1 mole of O2, I will also have 24.79 litres. Okay, and I also will have 6.022 times 10 to the 23 particles, same here. Okay, this is Avogadro's law. So basically 1 mole, 24.79 litres. If I have 2 moles of H2, the volume will equal 2 times 24.79 litres. We can actually use the term volume, and then we use capital M